So we're going to give this quantum mechanics stuff a go, and it's going to be ugly before it's over. I will say this. There was a fairly famous physicist not so long ago that said, every good quantum mechanicist is insane at heart. And that is where we're going to go down. We're going to go to the rabbit hole. And I need you to understand the following. The thing about this rabbit hole is it's unfortunately true. And almost nobody believes it when they hear it the first time. So as I run you through this, I'm going to explain to you the experiments involved. And if you come up with a better explanation, you can get yourself a Nobel Prize, because right now we're running out of things that make sense. So, as that is an introduction, let's talk about what we've thus far discovered. You've been told by your chemistry teacher, and same thing every chemistry teacher in America says, if you have an atom, whoops, I can't draw an atom apparently today. If you have an atom, boop, and you have an electron sitting here, you can put one more electron over here, boop, 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 and that's all you can do. And then there's another shell on the outside of that. You can put 8 electrons in. And sometimes I talk about S&P shells or whatever. We'll just go simple right now. We don't need to talk about chemistry. And that electrons can go on one shell or the other shell, but they can't go in between. As physicists, we scratch our head and go, why not? You can orbit in between those two. Why would there be some limit there? We also discovered that this thing is stubborn. If you shine a light on it and it's not enough to get to the next outer shell, this electron's not going anywhere. It'll happily go to the shell outside if you get enough energy for that. Or you kick it all the way out, but you can't give it a half amount of energy to get there because it will not go. And one thing I didn't mention last time, which is kind of interesting, is that these two electrons that work in pairs, those two objects, one of them spin up and one of them spin down. In other words, we can tell by the magnetic fields that one of them is spinning this way and one of them is flipped over and spinning the other way. Now, why must every set of electrons like this be flipped? There's no real reason for it. In fact, in playing with it, we found out that if you flip this one over, the other one flips immediately to the other side, instantaneously. In fact, it can be argued faster than the speed of light, which later I'm going to say is impossible. These two objects are linked in some fashion. They're paired. In fact, one of the strange experiments they've done recently is they actually went out to some islands, Canary Islands, went 10 miles apart. What they did is they took two of them, they put them next to a nucleus, they made sure that they were paired, they carefully separated them so they wouldn't flip over, left one in the laboratory, drove one in a boat all the way to the other island, then flipped this one over and watched this one flip back over the other way. They must be opposite spins. It's another experiment that doesn't make sense if you think about it for any length of time. So we move forward, because somebody has to do an experiment somewhere on this stuff. So the experiment comes in a different way, and it comes from this idea, a guy named Young. Now Young, again, this would be much better if we were like sitting in a classroom together. It would be much easier to explain all this stuff, but whatever. I can't show it to you here, but we'll give it a shot. That's the easy way to do it. All right, so Young was working with light. He basically put up a little barrier in a spot right here, and he fired light through the little hole, and light goes through the little hole, and it spreads out on the other side. And if you look at the other side, it's bright, and it gets dimmer on both sides. In fact, right here I have a picture of a single slit pattern. And again, there's some waves out here. I don't want to talk about those just yet. And then there's, if you have a two-slit thing, something really fun happens. Because this wave goes like this, and this wave goes like this, they interfere with each other, right? And we remember last year from interference patterns, that what happens is you get highs and lows. And where these two hit together, that'd be a super big high, right? It'll be twice as big. And so these become bright spots on the back wall. So you end up with bright spots, and then the dark spot, bright spot, dark spot, bright spot. And that's what this thing looks like. So when you fire a laser through 2 slits, this is what you get. We can do this at the school, so it's really not that big a deal with lasers. Okay? So while Young was working on that, another guy named Heisenberg was working on a completely different problem. His problem was this. He was trying to figure out how big is an electron. Seems like an easy enough thing to play around with. You got its mass, you got its charge. How hard would it be to figure out what an electron size is? Turns out it's very hard. Because as we discussed before, how do you know where an electron is? Well, you hit it with light. What happens when you hit an electron with light? It goes and flies away super fast. So imagine for a moment you've got a dark room and you're trying to find a butterfly. And you got 2 choices. You can fire a bullet with a gun. And maybe I should explain myself a little more. If I'm trying to find the electron, I can use infrared light, which is really big long wavelengths. Won't shoot it as hard, but look how big my wavelength is. Is it here? Is the electron here? Where's that electron? So I'm not really sure where it is. Or I can hit it with ultraviolet or gamma rays, in which case my wavelength's very small, so I know it's right here. But when I hit it, it's boom, I knock it out of here. So I lose information about where it is. Sorry, how fast it's going, right? Because I hit it so hard, it's obviously moving much faster than it was before and in a different direction. So it's like saying if you had a room with one butterfly in it and you were shooting you could choose, you could fire a high-speed rifle at it, or you could throw big old pillows. And from that, keeping the room dark, try to figure out where the butterfly is. Well, the problem is if you hit the butterfly, you've changed what it is. So Heisenberg was troubled by the fact that he had reached a limit on what he could do. He could not figure out how to figure out where an electron is and what it's doing at the same time. He couldn't figure out speed and position, so he started talking about the problem he had. He said, if I experiment on something, I change what it is. Okay, I'll give you an example. One of my favorite examples. I used to drive, when I was driving to work when I was living in Virginia, there was I didn't even know at the time, I was part of an experiment. And the experiment was done by the Virginia Highway Patrol. Virginia Highway Patrol was trying to figure out how fast cars were going because they were trying to figure out what they were going to do about a traffic management issue. So what they do? Well, they had to figure out how fast they're going. So what can tell you how fast it's going? Well, obviously, what you're going to use is a police car, right? Because it's got a radar gun. So you put a police car on the side of the road. I kid you not, this is what happened. Put a police car on the side of the road, and people were driving past the police car on the highway. And believe it or not, we discovered that the people in Virginia are very law-abiding, and they travel the speed limit at all times. And so therefore, there was really no reason for traffic management. Now, there was some suspicion that perhaps having a police car determined how fast the cars were going. In other words, the measuring of the speed changed the speed of the cars. So what they do next? Well, they put a van on the side of the road. So they put a van on the side of the road right next to the highway, so they could get maybe, you got to be pretty close to the highway to get to the. And there was a little guy hiding in the back, shooting things with radar guns. Okay, and so if you've got a car sitting on the side of the road, you're going to slow down, right? So although people were less law-abiding when there was a van over there, it still was pretty close to the speed limit because people were trying to worry about this little van over there. So finally, they got the really clever idea, and I actually saw this guy on the day it happened because it made the newspapers. There was a police officer. What they decided to do is they put a police car officer on an overpass, and they hid him behind some of the concrete things, and he was there with a radar gun shooting the cars as they drove underneath. Now, all that's well and good, but I saw him. And somebody else saw him, by the way, and called the police. Why? Because there was some guy with a gun on the overpass. Yeah. So, although this was the fastest speed, because apparently most people didn't see the guy up there, it changed the answer. And Heisenberg came to the conclusion, not because of Virginia Highway Patrol, but because in general, he said, if you experiment on something, you change the answer. If you're in a room and you're measuring the temperature of the room, you being in the room changes the temperature of the room. Even if you leave the room, the equipment you put in there is going to change the temperature of the room. There's no way you can experiment on something without detecting without changing the answer to the question. It's called the Heisenberg uncertainty principle. And it's particularly offensive in the case of electrons. Why? Because, again, to find what an electron is, you have to use light. Light is either going to hit it like a fast-speed bullet and blow it out of there, not telling you how fast it was going before it started, certainly not telling you how fast it's going after it gets hit, or you can use really big waves and hardly move the electron at all, but again, you don't know where it is. Radio waves have wavelengths of a mile. You're not going to know exactly where the electron is. And so this is a struggle. How big is the electron and how fast it's moving? And it turns out Heisenberg came up with a rather bizarre statement. He said, you'll never know. He said, look, no matter what you do, the limit is you can only know the momentum, and the position. Error in position, the error in momentum, that is always going to be greater than some number that because Heisenberg, he put an H to it. And he said, and that, by the way, that's the limit. There's nothing you can do. You're never, ever going to know. You can't peek in that box. And if you smash one of these two values down, the other one goes up. If you figure out the momentum really well, then you're going to lose information about the speed. And so Heisenberg came under the conclusion that the bottom line is we're never going to know exactly what we need to know about electrons. Now, that doesn't sit well with people. And amongst those people, it didn't sit well with this guy named Young that I brought up earlier. He was doing those light experiments. And he said, well, I could do the same thing with an electron. I could make my little thing smaller and smaller and force my electron through my tiny little hole. And I could tell a lot about how fast it was going based on that. So he builds himself an electron shooting spitting machine. And as he's building this, he builds a wall, basically essentially a magnetic wall. As electrons go shooting through this, he's got a glass tube in the back. And that glass tube was phosphorus in there. And so the electron hits here. And he was starting to do measurements that involved, and he got that most of them hit right dead center, a couple of them hit a little farther left, a little farther right. So the glow was very much like a single slit pattern, as you'd expect it to be, because there's only one hole and electrons going through that. It's not a wave, so it's really not going to be an issue. So he was really excited about this, and but unfortunately, the more he smashed this down, weird stuff happened. When he got it too small, the electron refused to go through the hole. Or when it did, it made the exact same pattern, which led him to struggle with what the heck is going on there. So he shared this information with everybody, and there's a lot of people going, that's interesting, but not all that bad. And along comes Albert Einstein. Albert Einstein very cleverly notes that maybe this isn't a big deal because it could be a probability thing. So he says what he suggests you do is just, let's go ahead and shoot 2 through and see what happens. And so our boy Young fires electrons in double slits, and he gets this pattern here. What? Why is this pattern made? Because it's waves. Electrons aren't waves, they're particles. Why is it making this pattern here? More in a second. Video 2.